Okay, I said before that we are using voltage transformers and current transformer in order to reduce the voltages and current and go into the distant relay. As I said before, it's very important that you must be able to translate the variables from the primary to the secondary or to the relay side. Okay. In this case, let me present a short example. It's extremely short, but probably useful. Imagine that we are working with a transmission line, okay, and the relay that we are using is connected to a current transformer, and the current transformer has a transformer ratio 500 to 5, okay? As you can see, this American one is 5 amps on the secondary, and here we have a voltage transformer, and the turn ratio is going from 20,000 to 63.3. That is the voltage transformer ratio, okay? The impedance of the transmission line in this case is 8 plus J32 ohms. Of course, that is the impedance of the transmission line, and that means is located at the primary side of those transformers. The question here is extremely straightforward, is determine the value of the impedance line as seen by the impedance relay, okay? What we need to do is that we are using here voltage and current transformers, and we need to define what is the what the transformer ratio is, okay? And here for the transformer, for the current transformer, 500 to 5, transformer ratio 100, and then we have the voltage transformer, 20,000 to 69.3, that is around 289, okay? And then the impedance conversion factor is the ratio between the current transformer ratio and the voltage transformer ratio, okay? What I'm trying to say is here you can see and set that is the impedance conversion factor, dividing 100 by 200 by 288. We obtain over here 0.34. That is the impedance conversion factor, okay? What we need to do now is taking the impedance of this transmission line from the primary to the secondary, and using the impedance conversion factor, we got here 2.72 plus J 11.08, okay? What you can see is that those transformers, because the transformer ratio, they are reducing the impedance from the transmission side to the relay side, okay? Um, More discussions about the connections and more discussion about more complicated cases depending of the connection of the current transformer and voltage transformer, go to my class about CT and VT, okay? What I will do now is a very small discussion about load conditions, okay? Um, um, Load conditions, they can affect the operation of the distant relay, okay? A distant relay, you can imagine a distant relay like a control system. They are taking measurements or they are sensing all the time. I mean, a distant relay is connected to the system and it's receiving signal from the VT and the CT all the moment. That means that when we are working, when the power system is working in a steady state, there are currents and voltages over there, and the impedance relay is calculating the ratio between the voltage and current, okay? Of course, when we are in short circuit conditions, voltage, they try to depress, the current try to increase, and the ratio between voltage and current is a bit different, okay? However, when we are on low conditions, what is happening with the relay, okay? Well, what you need to understand is any distant relay is sensing voltage and currents on the secondary of the transformers, okay? That is the first thing that you must understand. And it's not only during fault condition, it's all the moment, including a steady state, including overload. All Every single second, the relay is receiving signal from voltages and current, okay? What is interesting to understand is that the load current is several times below to the short circuit level. And in that consequence, for instance, for very light loads, what is happening is that the current is very small, and that can produce some circles that they are bigger than the operation uh, of the impedance or distant relay. Okay, I believe you can see here there are two circles, one big, that is the possible operating area coming from light loads or very small loads, and then we have a smaller cycle, and that is coming from heavy loads. Okay, um, what is the idea? The idea is that we need to identify clearly the load conditions, lights and load, and heavy, sorry, in order to be careful and identify if there is any possibility that the load current create voltage profile that the impedance, the amperant impedance, go inside the tripping zone. Okay. Um, Typically, what we need to take care a lot is looking into emergency conditions on transmission system. During emergency conditions, the current transmission line could be bigger than the normal load current, and that can create some impedance seen by the relay that could be smaller, and we need to be sure that the relay identify those relative medium to small impedances as normal conditions uh, and not as a short circuit. Okay, I have a numerical example here to told you about low conditions. Okay, here you can see we have a transmission line, the transmission line AB. Okay, they are transmission line A to B. We know the impedance, and also this is a medium-sized transmission line, and there is a charging current of 50 amps. Okay, what is the charging current? Well, if we have this transmission line without any load, um, this transmission line is taking current from the system, and the current is 15 amps. And what is the use of that current? Okay, that current is the current going across the shunt capacitance in the transmission line. That is the reason that is a very small current, but is very, very capacitive current. Okay. Uh, for this transmission line, we know some load conditions. In this case, the load is 8 MVA, the voltage is 20 kV, kilovolts, and the load current is 400 amps, okay? In this case, we will focus on the relay located here on terminal B and tripping the circuit breaker A, okay? And they are over here a voltage transformer 20,000 to 69.3, and we have over there also a current transformer, American current transformer 500 to 5. Okay, now the interesting question here is we want to create the representation of this system in the Rx plane. Okay, that is what we want. We want to create the plot on the resistive reactant plane in order to show you all the effects coming from loads and faults. Okay, what is the first step? Okay, the first step is we have nominal load but we can say for this moment that this load is basically a static load. We can say that that load is an impedance, and what we need to know is this impedance is dividing voltage and current. We are assuming that this is a line to neutral voltage here, and we have 20 divided by 400, we have 50 ohms, okay? Then we are using the impedance transformer ratio here. That is the ratio between the current transformer and the voltage transformer ratio, and then multiply by the primary apparent load. And what we obtain here is the full load at the secondary, and this is 13.86 ohms, the resistant component, and the inductive reactance is 10.39, okay? What I'm trying to say is this is the case of assuming that we are using a lagging power factor. We are assuming that is a lagging factor of 0.8, okay? What is my job now? Well, my job now is, okay, but what's happening if the power factor of this load is not lagging? Instead of lagging, this is a leading power factor. Well, if this is a leading power factor, the consequence is that the reactive component will change the polarity. And now we have here the load number 2 representing a leading power factor, and this is 13.86, that is the resistive part. And the reactive part now is a capacitive reactance, and it's 10.395, okay? It's the same value, but the polarity change, okay? If you look on the right-hand side, what I am doing is start to plot the points representing the load when we are assuming there is a lagging power factor, and that is the point load 1. And load 2 is when we are having a capacitive power factor, okay, or leading power factor. What is on the other side? Well, on the other side, we can see the load 3 and 4. We can see the load 3 and 4. And the load 3 and 4 represent a change on the load flow direction. What I'm trying to say is that load 3 and 4 represent when the power flow is moving from B to A, and that means a change here at the load location on the negative side of the resistant axis, okay? And over there, as you can see, those 4 points, they represent the load condition for several load flow directions and for the power factor of 0.8 leading or lagging, okay? If you make a more detailed analysis, you will realize that the line that's supposed to describe the interconnection of more power factors, it's supposed to be a circle, and that was the reason that we present a circle to represent the load in the previous slides, okay? But now what we need to do is, okay, let's do the following. Let's refer the source impedance from the primary to the secondary of the voltage and current transformers, okay? And in this case, what we will do is the following, okay? Using the impedance transformer ratio, you can see over here, we obtain we easily obtain the source impedance, positive sequence, and the negative sequence for the source, okay? And in the transmission line, I can see over here using the impedance transformer ratio. Here you can see the impedance located at the secondary. Okay. Okay, but now the question is the following: if we are working with a distant relay, um, we used to use a phrase that is we used to say a terminology that is extremely important, okay? Imagine that we are working with the relay RAB that is located at bus bar A, and we want to identify faults that they are inside the transmission line, okay? Well, what we need to do is define what we call a protection zone. In this case, I will call the zone number 1 to identify faults inside the transmission line. Typically, the zone number 1 is referred like between 85 to 90% of the total line length. In this case, we will use 85% of the total impedance. Okay, that means 85% of the total impedance. That is around 0.85 multiplied by this number over here, and we obtain this is the impedance at the primary of this zone. Zone number 1 is 85% of the total impedance of the transmission line. That when we refer to the secondary, we obtain that we have a setting for this distance relay of 1.17 plus J 9.4, and that is the setting for the zone number 1, or the underreaching zone of this distance relay. Okay. Okay. What I am presenting here is the following. What I am presenting here is, okay, as you can see, we have the red plot, and that represents the loads that we already presented. And in black color between A and B, what I am presenting is the total impedance of the transmission line. Okay. What I am presenting here going down is the impedance coming from the source number 1. And what I am presenting between B and S2 is the impedance coming from the source number 2, okay? If you come back here, I have two sources. One source is S1 and the second source is S2, okay? And here you can see the impedance for the source 1 and the impedance for the source 2, okay? This plot between A and B represent the transmission line, and from A to this point over here, that is the setting for the zone number 1. As you can see, this is the total transmission line, and approximately, if you use the proper scale, you will see that this point over here is 85% of the total impedance of the transmission line. This small dot represents the setting for zone 1 of the relay that is looking the transmission line AB, okay? And what is the small over here? Well, we have another distant relay. You must remember here, let me come back to the original. We have the relay BA, and the BA is looking into the transmission line AB, but from the other side. That is the reason for the name RBA. BA means that this relay is looking from B to A, okay? Well, coming back here to my explanation of this graph, the dot over here means the settings of the relay AB in zone 1, and that is located 80% of this transmission line. But the other relay is 80% of the impedance, but is looking from B to A. That is the reason that the other point here, the point defined in the zone 1 of the relay BA, is located at 80% of the impedance, but on the other direction. Okay? Okay, now there is just a consideration. Okay? Red points then represent the loads. Okay, we have here lagging power factor, leading power factor. Here we have change of directions. Okay, but what you can see is if we plot a circle over here that is bigger than the circle defined by the impedance of the transmission line. And also, what's happened if the circuit breakers, I mean, if the transmission line is unloaded? Well, if this transmission line is unloaded, that means they are not load. However, because this is a mid to long transmission line, we have some current that receives the name charging current, okay? And the charging current is 15 amps. We can identify what is the impedance that is representing that 50 amps. In this case, in primary quantities, it will be 1.33 ohms. But if we refer to the secondary of the CT and VT, we obtain a big 461. As I say to you, the charging current is mainly a capacitive current, and that is the reason that you can see a big line here going to the minus x-axis with minus 461, and this point over here represents when the transmission line is unloaded. That represents the apparent impedance that the relay see. Okay? Okay, what you need to understand here is loading conditions, they can interfere with the operation of the distant relay. For that reason, in the future, when you are setting distant relay, it's very important that you also examine possible locations of loading conditions, especially emergency loading condition of transmission lines. They can produce impedance relative small that can go inside the circle defined by the distance protection, and they can groundly trip the distance protection. Okay. Okay. As I said before, the load conditions can go inside the circle. What is an option? Okay, one option is okay, instead of using a circle, we can use another kind of characteristics. And to be honest, that is the motivation that start to create some different distant relays characteristic. Okay. As you can see over here, there are at least six different characteristics. Okay, I highly suggest that you go and read the IEEE C37113. Okay, the C37113 is very important for you because that is the guide for protective relay applications to transmission lines. Okay, over there, if I am correct, in section 6. You will find a specific location. Let me try to remember. I think it's 6 point. Well, I don't remember. But inside the IEEE C37, you will find those 6 characteristics, okay? The description of those 6 characteristics. Mainly, we will find the classical impedance characteristic, that this is the one that I have been discussing from the previous probably 20 or 30 minutes. It's typically the circle, and the origin is at the the center of that circle is located at the origin of the RX plane, okay? That is this one over here. You can see is the beautiful circle and is totally symmetrical, referring to the origin of the ets r ets plane. Okay. The next characteristic is the mode characteristic. I remember during my second class, I was talking about operational characteristic of different relay, and I discussed the mode characteristic. The mode characteristic is quite interesting because it's used to introduce some directionality into the distance protection. Okay, and in this case, the circular shape or characteristic of the relay is passing by the origin of the RX plane. Okay, what is the idea of this characteristic? Okay, the idea of this characteristic is if you have some load conditions here or some load conditions there, what you need to do is use a mode characteristic and you will separate or put some impedance distance between the load conditions and the operating characteristic of your relay, okay? Here is the rectangle characteristic that is coming basically for the use of a line that is parallel to the R axis. That is the classical reactance relay, okay? On the right-hand side, you will see one that is quite interesting. That is the quadrilateral characteristic, okay? It's basically four lines that we can connect each other and they define the operating zone, okay? To be honest, the previous characteristics, I mean the impedance characteristic, the mode characteristic, the reactance characteristic, they can be obtained using the classical electromechanical relays. However, the quadrilateral characteristic is not possible. The quadrilateral characteristic start to be popular and be in the market after the solid state or computer relays appear into the market. Okay, what is the idea of this strange characteristic? Well, the idea of this strange characteristic is that you can get flexibility defining the corners of that quadrilateral characteristic, and that adds you flexibility at the moment of coordinating multiple distance relay. Okay. There are two more, and you can see full explanation at the IEEE C37113, specifically at the section 6.2.4. And there is one that is called the lenticular characteristic. It's mainly similar to the mode characteristic, but instead of having the circular shape, in this case you have like two circular areas that they intercept each other, and inside the intersection you have the tripping area, and outside you will have the block area. Okay. And finally, most recently, solid state relays, they have evolved, and right now you can define almost any characteristic that you want, defining different lines, different shapes, and that is what we call the polygon characteristic. Okay, the polygon characteristic is basically one characteristic that can be tailored for any specific application, and that is very powerful when you are dealing with very complicated distance protections. Okay.